Okay, so today we are going to deal with infrared spectroscopy. We have seen the basic principles behind this, but today we will go into a bit more detail. Okay, so now I'll just summarize what we learned in a couple of slides in the second lecture. So we have molecules that consist of atoms, and the bonds are generally formed by atoms sharing electrons between them. And depending on how much is the extent to which electrons are transferred between one atom to the other, you have dipole moment created. And as we saw before, these bonds, they're not static, they're always vibrating. Okay, and if the molecule that we start with, if the bond itself has a dipole moment, then this vibrational modes, they create a fluctuating electric and magnetic field, and that can couple with the electric field of the incoming radiation. And when that condition happens, then there's transfer of energy, and that's when absorption happens. Okay. There's one thing that I mentioned, that we have molecules that have a dipole moment to start with. Okay, the bond is already polarized, but there are molecules that are not polarized, but then during the mode of vibration they become polarized. They develop a dipole moment very momentarily, and even they absorb radiation, infrared radiation. Okay, I'll give very specific examples of these kinds in next couple of slides. If you take a bond between two atoms, we have the following characteristics of a vibrating bond. Okay, the energy of vibration is directly proportional to the frequency, and the frequency of vibration is directly proportional to the spring constant K. It is also known as force constant. The way we see atoms in a bond is two masses connected to each other by a spring. So this is equivalent to a spring constant in the classical two spheres bonded together by a spring which is vibrating. Okay. So frequency is directly related to the force constant, and it is inversely related to the reduced mass. Mass, if the atoms are heavier, they're going to vibrate at much lower frequencies. That is what this means. Okay. So if you have two atoms that are lower mass when compared to two other atoms that are having larger mass, then you can expect some higher frequencies of vibration from the bond that consists of lower mass atoms. That's the conclusion of this. The thing that one has to conclude from this is that the bond strength is directly related to the frequency, as I mentioned before, and the mass of the atoms is also very important in deciding what the frequency is. Okay, now let's look at how an infrared spectrum is actually recorded. We saw a very simple schematic in the lecture 2, where we send we have a source of light that can produce a range of wavelengths, and its intensity is I0. We have a sample which consists of molecules which have bonds that can absorb infrared radiation, and then the light, as it passes through, some of the radiation is absorbed, and the transmitted intensity is I, and the detector detects the difference between I0 and I. Okay. Now, the infrared radiation, it has the following range. The wavelength is around 0.8 micrometer to 100 micrometer, but the range that we will be using, the useful range for infrared spectroscopy, that is the mid-infrared region, which goes from 2.5 to 25 micrometer. Okay, how does a typical infrared spectrum looks like? You have absorbance, as I mentioned in the previous slide, and you have different wave numbers, which is a form of frequency. I will explain in the next slide why are we using wave numbers instead of hertz. Hertz is the standard unit of frequency, but here we are using wave number. I will tell in the next slide why. So now you have absorbance versus wavelength, But then for infrared spectroscopy, we don't use absorbance as such. We convert that to transmitters. And this is how a typical infrared spectrum looks. So you have a molecule. Let's say the molecule has a lot of bonds. For example, it's a CH3, CH2. So there's a C bond here, C single bond C. And then here there's a carbonyl bond. So if you record a spectrum, you will find peaks that correspond to some of the bond vibrations in this molecule. Okay, by looking at these peaks, you can tell, okay, there were these bonds in that molecule. Okay, here is the reason why we use wave number instead of frequency. Let's take the mid-infrared region. In microns, it goes from 2.5 micrometer to 25 micrometer. Let's say, I'll just give a rough estimate of total number of bonds that you will ever come across in entire chemistry. Okay, let's say it's 1,000. So you have to detect 1,000 bonds between this range. Okay, so now you can see that there are only 20 units between these two numbers. So they're going to be too much crowded. Okay. Now if you go to hertz, then you have 120 to 12 terahertz. So you're going to deal with a huge number, a number that is 12 digits. Okay. And the other option is we convert it into centimeter inverse. So now 2.5 micrometer corresponds to 4,000 centimeter inverse, and 25 micrometer corresponds to 400 centimeter inverse. Now if you want to fit in 1,000 bonds between this, it's pretty straightforward, right? So that's the reason why scientists, when this technique started, they started using centimeter inverse. Here is an example how this centimeter inverse, the wave number, is calculated. Now the velocity of light is lambda multiplied by the frequency, the wavelength multiplied by frequency, and you have the frequency is inversely proportional to wavelength. Quite obvious. Let's take an example. Let's take a wavelength of infrared radiation that has 2.5 micron wavelength. Okay. Now that corresponds to 2.5 into 10 power minus 4 centimeter. Now frequency is inversely proportional to lambda. If you calculate 1 by wavelength in centimeter, 2.5 converts into 4,000 centimeter inverse. Okay, so that's how you convert 2.5 micrometer to 4,000 centimeter inverse. This also applies to Raman. I don't know if you remember Raman spectrum. You had wave number on the x-axis. Okay. Now let's talk about what kind of molecules. Somebody drop this. What kind of bonds, what kind of vibrations lead to absorption of infrared radiation? Okay, let's take a hypothetical molecule. It's not a hypothetical; it does exist. Let's consider only this group, CH2. So this is the carbon, and these two are hydrogens. Okay. Now, since they are vibrating, they can vibrate in all directions. Let's first consider the symmetrical stretch, where all three atoms are moving away from each other. Okay. Now this is called symmetrical because all are moving away from a central point. Okay. Now it has a vibration of frequency of around 2,853 centimeter inverse. If you see, there is a small nu with subscript S. The S stands for symmetrical. And AS, symmetrical stretch, and AS stands for asymmetrical stretch. Okay. And asymmetrical stretch has this absorption frequency. Now you can do these calculations and then theoretically calculate what all kinds of vibrations lead to. Now here there are two types of vibrations. One is stretching, where the bond length changes. The other is bond angle. Now the hydrogens, they come closer to each other, and the carbon atom, it moves away. So it is a kind of combination of stretching and bending. Okay, and here are the absorption frequencies of these. As a rule of thumb, it is generally observed that bending vibrations have much lower frequency. If you see, this is a very good example of bending vibration. It has 720. Stretching, in the previous slide, if you see, they're close to 3000 centimeters. Okay, so these are different types. This is pronounced scissoring, this is pronounced wagging, and they behave almost like people with two hands. So they are having all kinds of motions, and they have very specific absorption. Each of these vibrations absorb very specifically in the infrared region. Okay, now I'll give one example with the spectrum. In the previous slide I gave just examples, wave numbers. Now this is cyclohexane, which is a cyclic molecule with 6 CH2 groups. And if you record a spectrum, this is what you will find. On y-axis you have transmittance, and here is the wave number. And each of these peak corresponds to either a symmetrical stretch, asymmetrical stretch, bending, rocking, wagging, all these kind of. And one thing that you can clearly observe is this intensity is higher when compared to this. This is even higher when compared to this. So there are going to be bonds that have specific vibrational modes that give higher intensity. The same bond will have vibrational modes that will give lower intensity. Okay, so these higher and lower intensities, they are denoted by the term strong, medium, and weak. If, for example, the CH2 stretch in this region, in infrared spectroscopy, it is going to be a strong peak because it gives very high intensity. But if you take this molecule and record a Raman spectrum, then most likely, it may not be true, but most likely this intensity will reverse. This, which gives a very strong peak in infrared spectroscopy, will be weak in Raman spectroscopy. Okay, maybe this will be the wagging and the twisting. Maybe that is of higher intensity in Raman. Okay, yeah, I mentioned that. So you have peaks that correspond to vibrational modes of bonds that are in the molecule, and the intensity difference is due to the efficiency with which they interact with the infrared radiation. Okay, now let's take the most important molecule of everything that is available on Earth. It's water. Now you have couple of modes of vibration. Okay, this is not infrared active. I don't know why I removed it. Okay, doesn't matter. This bond, it does absorb, okay, in infrared region. Okay, so now if you take, there are two things. One is where this is a bending vibration and this is a stretching vibration, and you get peaks corresponding to that. This is the bending vibration and this is the stretching vibration. Again, bending is at a lower frequency and stretching is at a higher frequency. Okay, one huge conclusion from this slide is, if you see the hydrogen OH stretch is, sorry, this one, OH stretch is very broad, very huge. So if you have molecules that can exhibit the CH stretch, that also comes here, okay. And if you go here, if you see CH is very sharp, okay, and this is so broad that if you have molecules, organic molecules, and with little bit of water, you will lose this whole region. The OH stretch will envelope the entire region. So you will lose all the information that you are supposed to get here because of OH stretch. That's why in infrared spectroscopy, you will always be advised that dry your sample thoroughly so that you don't get interference from this. This is one major difference. In Raman, you don't have this problem. Okay, in Raman, you can have a wet sample. You can actually do in situ measurements. That's what Thomas was telling the other day, that you can follow a reaction in water. But in Raman, in infrared, water is a must to be removed. Okay, two IR bands, yeah, samples should be measured without water, that's what I said. Okay, here are some more detailed classification of bonds. You have water, and you have symmetrical and asymmetrical stretch, okay, and some of these bonds are, all these bonds are active, but some give higher intensity, some give lower intensity. Okay, now I'll take another classical molecule, which is carbon dioxide. In the previous water molecule, okay, each of these bonds to start with, they are already having a dipole moment, and since it's not a linear molecule, it's a V-shaped molecule, so the dipoles don't cancel each other. But in the case of carbon dioxide, the dipole moment, the carbon-oxygen bond, it has a dipole moment, but these two dipoles are opposing each other, so they cancel each other. Overall, carbon dioxide molecule does not have a dipole moment, okay? But the molecule, even though overall it does not have a dipole moment, there are bending and stretching modes that have a net dipole moment. So carbon dioxide does absorb in infrared region. Okay. Here are some examples. For example, if you take the asymmetrical stretch, okay. Now, as I told you, the two dipole moments cancel each other. But here, because the two dipoles that are existing, the values itself is changing, then the net sum of that won't be zero. Okay. And that is the reason why this asymmetrical stretching of carbon dioxide will be infrared active. Okay. So now, for example, the symmetrical stretching, where the two oxygen atoms move away from carbon, this is exactly the same thing as this. So the two dipole moments created, they cancel each other, even though the actual dipole moment value for each of these bonds is higher than here, but they cancel anyways. Okay. On the other hand, when the oxygen moves in one direction the carbon moves in one direction while the oxygen moves in the opposite direction. Now here the molecule is no longer linear, so the dipole moments won't cancel each other. There will be a net dipole. This will be infrared active, infrared active, infrared inactive. And so here is the infrared spectrum for carbon dioxide. Okay, there is some water mixture. If I'm right, they just took atmosphere and then they recorded the spectrum. If I'm right, I might be wrong. Okay, so there is some water contamination, but then other than that, you can see very good asymmetrical stretch, and there is a carbon dioxide bend. And what about symmetrical stretching? If you do Raman, most likely you will find this peak there. Okay. So now it's very clear that if you are looking for some peaks, and if they're not there in infrared, most likely they will be there in Raman. Okay, I will give you now what we'll do now for next, let's say 10 minutes, is we'll take very simple molecule and we keep adding complexity to it. Okay, and then see how the infrared spectrum changes. First, let's take the simplest molecule, which is a bunch of carbons bound to each other. Okay, it's just an alkane. It's, I think, dodecane. Okay, so now you'll have characteristics of CC stretch, CH stretch, okay, and that's all you'll see here. So this is the CH stretch, CH bend, and you have CH rocking. And depending on how efficient they are in absorbing, so the intensity changes, the position changes, depending on the energy of vibration. Okay. So now we'll take alkane molecule, add, let's say, one hydroxyl to it. So now, apart from CH, you also have a OH and CO. Okay. So as soon as you see a molecule, you have to break that into bonds. Just split it up into what all bonds are available. Okay. And then you will look for the corresponding bonds in either Raman or infrared. So now, if you see the CH stretch is pretty narrow, okay, but then OH has become very wide. If this sample had a little bit of water in it, this whole region will be one peak. So you will lose this information. Okay, now we have the OH stretch, CH stretch, and CH bend. And you also have the CO stretch. Okay, so now we have added one hydroxyl to this group. Let's increase the complexity of this molecule. Let's make it aromatic. Okay, so aromatic is where you have C double bond C. Now you have the OH, okay, and then you have the C double bond C, as I told you, and you have the OH, you have the CO. So every bond, if it is Raman active, it will show up on your spectrum. And so if you get an unknown sample, okay, and you see these peaks, that means you have these bonds in the sample. If you have the molecule, then you can predict the spectrum. It works both ways. Okay, so now let's have a carbonyl group. Okay, so you will, in the previous slide we had C single bond O, so now you have introduced a C double bond O, and you have peaks corresponding to that. Okay, C double bond O. This is very important for plant materials because all polysaccharides, they have a carbonyl group, and that's a C double bond. So you will, most of your plant samples you will find a C double bond O if they have polysaccharides. Lignin, when you have lignin, you have aromatic species or unsaturated carbons, then you will find the CC, not ring, but just alkene stretch. Okay, so now from carbonyl we'll go to carboxyl. Okay, so now you have a carbonyl, and we also attach a hydroxyl to it. Now you get CH and you have OH, they have both clubbed together, and you have a CO stretch, you have a OH bend out of plane, and all the peaks will correspond to the bonds that are here. That's the point that I'm trying to make from all these examples. Okay, now we'll also look at NH. Okay, now what is the new bond that you'll expect? Okay, so in the previous you had, when you introduced the hydroxyl, you saw OH, right? And here you're introducing NH2, so you will expect a NH. Is there NH here? Yes, you have NH. And there is also a CN bond, okay? So that is new, so you will find a CN stretch. The one thing that we need to observe is the CN stretch is very low intensity, okay? It's not that strong. Okay, there is CH stretch, CH2 scissoring, NH bend, NH wagon. Okay, one other thing when it comes to carboxyls is that the carboxyls are capable of forming intermolecular hydrogen bonding. Okay, inter is between two. So you have the hydrogen of one carboxyl being shared by the oxygen of the other. Okay, and this leads to a stronger affinity, and the OH stretch or bend, it will be affected by this bond. This hydroxyl is no longer, this OH is no longer that free to vibrate if it was just alone. Now this is influenced by this oxygen, so its vibrational characteristics will change, and that's what we are observing here. Here we have for the carboxyl, let's say you recorded this in a gas phase where the molecules are not interacting with each other, or let's say in diluted solvent. Okay, now you have a clear OH and you have a CH. On the other hand, if you take the pure carboxyl containing molecule and record that as a neat sample, which means just take 100% liquid of that and then record it, you find that the OH peak has broadened a lot because of this intermolecular hydrogen bond. Okay, so now we've seen CH3, okay, and then we added hydroxyl to it, we added carboxyl, we added carbonyl, we added amine, we added carboxyl, okay, and we also saw aromatic phenol. So now, if you analyze all these compounds, then you will see that most of these bonds, they will fall in one range of values. So you can come up with this general table where you can tell all the OH hydroxyls from your any molecule that you take, they'll fall in this region, OH and NH. But then, of course, you know, OH stretch, I'm talking about OH stretch. If there is OH bend, they'll come somewhere here, lower. Okay. So by OH and NH, in this region, I mean stretch, OH stretch. And here, CH stretch, again, it comes at around 3000. You have C carbonyl in this region, olefin, which is C double bond C, as it's written there, and then aromatic. And so now we have a general idea of where to expect peaks if you have some specific bonds. Now, from there we'll go to some molecule that has a lot of relevance to all of us, which is cellulose. Now, as soon as you see this structure, okay, so you should be able to guess what kind of stretches, what kind of bending, what kind of bending, rocking you expect from the spectrum. So now you have, one thing is you have a lot of hydroxyls, okay, so you will find an OH stretch, OH bend, and you have a C here. If you see there's a CO, so you will also find a CO bond. And what else is there? Okay, that's pretty much very basic. Okay, now you can look at the spectrum and you'll find there's a OH, CH, and there's CO, and these are the ring structures. Okay, and there is also a bit of water. Yeah. Okay. Yeah. So now infrared spectroscopy can be used. If you know the structure, we can predict, and we can confirm the structure. If you have a structure in mind, we can check if it is true or not. Now, here is an example where we are doing a small chemical modification. We are converting the hydroxyl to a trimethyl silyl group. Okay, so now we are going from OH to OSI. So now, if you look at the spectrum, you have to find there's a new element. That means there's going to be new bonds around it. Okay, so now you have SiC bond turning up, which is due to the presence of this, and OSI that also will be there somewhere here. Okay, so now this is a very quick example of how, if you do a very simple modification, if there's a change in bonding environment, we can detect that. Okay, here is an example how we use infrared spectroscopy to follow a reaction to a nanoparticle. Okay, you have a cellulose nanocrystal, and we have carboxyl surrounding it, and let's say at pH 10, which is higher than the isoelectric pH of carboxyl, all the carboxyls are negatively charged, and we have a cationic surfactant molecule, and the cationic molecule will bind to the anionic carboxyl, and it will form a cellulose neutralized with this cationic surfactant. Okay, so now if you want to follow whether this reaction has happened or not, there are a lot of differences between your starting material and this. That's exactly what you need to figure out when you want to use infrared spectroscopy. Okay, so now how do we follow this reaction? Look at all the bonds. Okay, so now in the previous slide I showed you cellulose, structure of cellulose, right? And keep that in mind. And then this is the reactant that you're adding. So all that you need to do is to find out, is there any bond differences? Are you introducing any new kinds of bonds by introducing this molecule? I can tell you in the starting material there was no nitrogen, okay, but in this molecule there is nitrogen. So that's a huge difference. That's a good starting point. So now cellulose, the short form from a cellulose nanocrystal is CNC, and the cationic molecule is C18 because it has 18 carbon atoms. For example, the number of CH2 groups, cellulose glucose molecule, it does not have that many CH2 groups. On the other hand, this one has around 16 in each molecule. Okay, so the proportion of CH2 groups is going to increase in the final sample if the reaction is happening. So now CH2, if you remember, it gives a very high intensity infrared stretch. Okay, so now if this reaction goes through, you will find the peak corresponding to CH2 groups increase if the reaction is successful. And the other thing is, like I said, the CN group, that is something new that was not in the original sample. So you will also find peaks corresponding to CN. Okay. Now, we have gone through this process, we have checked what the bonds are. Okay. Now, we need to look at, so we know the bonds. Okay. So how do we know which bond to look at? I mean, where to look at in the spectra. So what we do is, I hope the internet works. method is going to work. Let's just wait. Okay, so now you go to a database. Okay, it can be online, it can be a book. Okay, so now what you do is, so now if you remember, we figured out two differences. One is the CH2 group increase and the CN. Now look for example, CN stretch. Okay, sorry, it's here. Okay, so now these are the IR peaks. These are the regions where you will find here you tell, here it's telling whether it's a stretch or a bend. Here is the actual bond that you're looking at, and here is the region where you'll expect it. And like I said, some bonds are very high intense, some are very low intense, and that's what they mean by strong, medium, and then you have weak. Okay, and some they even mention that it's not present. Okay, so now let's say CH stretch. So we have to see strong, it says strong, and then CN, where is CN? Yeah, and CN stretch, it's medium to weak. Okay, and there's one more link that, now see this is only infrared spectroscopy, but then it's always good to compare. Use Explorer. Like I said, these techniques, Raman and infrared, are complementary. Okay. Now let's say you end up with a list of bonds, let's say, and they all are infrared, weak, not so strong. Then what you need to do is go look in Raman catalog and see if it is strong. If you see the SS bond or CCl bond, some of them, they both are strong, but generally if you see there is one strong, the other is weak. So you have a comparative peak intensity here, whether something is strong or weak. So in our previous slide that I showed, you had two examples, two differences. One was CH2 and CN, and CN we already saw that it's either weak or medium, but the CH stretch, that was very strong. Okay, now let's look at the spectrum. Okay, now here you have the cationic surfactant itself. This is the infrared spectrum of this molecule, and here you have the CNC, which is the starting material, and what they are doing here is increasing the ratio. Okay, the CNC is to the surfactant ratio. They are increasing. One big difference as you move from here to here is the appearance of this CH2 stretch. Okay, so that's one thing. Symmetrical and asymmetrical, you find both, and you also find that this is the carbonyl peak, the C double bond O. If you see, the carbonyl peak has shifted a bit. The reason for that is the carboxyl, it's no longer the same. Here it has been bound to cationic nitrogen. Okay, that changes the vibrational frequencies. And so now when you take a starting material and when you do modifications, don't expect the peaks to be exactly where they are. They move around a bit, and you should be able to interpret them and explain why they have moved either to higher frequency or lower frequency. Okay. So this is one example where we can follow this reaction using infrared spectroscopy. Okay, that I've covered. So now I'll give one more example where we are going to study a polymer. Okay. The simplest example is, I can give you a hypothetical example. Okay, if you take two polymers, that are compositions are completely different. Okay, it's very straightforward. For example, you're mixing, let's say, cellulose with DNA. Okay, cellulose does not have any phosphorus. DNA has the P double bond O bond. Okay, so that's very straightforward. I will give you a bit complicated example where the molecules structurally they are very similar. The polymers are very similar. Then how do you go about finding out how much of each of the polymer is there? Okay, now we are going to study how to characterize a copolymer. For that, let's just recall what a polymer is. If you take a monomeric molecule and attach it head to tail and continue the reaction, then you will end up with a polymeric long chain molecule. Now we are considering only linear polymers. Okay. Now let's say instead of just one monomer, you have two monomers, and here the monomers are perfectly alternating. Okay, so it's AB, AB, AB. But then there are also polymers that are random polymers where you don't have the condition where the polymer B has to follow a A. It does not have to be like that. They can follow any of these two they want. And that's mostly statistical probability, based on probability. Now let's take ethylene, propene. These are some of the most common polymers that human beings use. And ethylene upon polymerization becomes polyethylene, propene becomes polypropylene. Okay. Now if you look at these two structures, they are very similar except for the difference that there is a CH3, but there is also CH stretch here. Okay, so now in terms of infrared spectroscopy, these two are very, very similar molecules with very small difference. Okay, so now you can see that there is methyl groups. Okay, now when you do a random copolymer, you can imagine this to be a combination of polyethylene and polypropylene. Okay, so now what we want to do is, let's say you're mixing these two polymers and you want to find out how much of this monomer is there, how much of this monomer is there. And that's the problem that we are going to deal using infrared spectroscopy. Okay, now these are two infrared spectra. This is where PE stands for polyethylene, PP stands for polypropylene. You have 85% polyethylene, 15% polypropylene. Here you have, when compared to this, you have higher polypropylene percentage. Now, if you see, the difference between this is very, very small. Okay, so now let's go to the typical regions. Here is the CH stretch. In the x-axis you have wavelength in microns, but if you look above, okay, it's in wave number. So you don't have to be confused that it is in microns. Okay, you can look up. Okay, so now the CH stretch, the CH bend, more or less they are similar. One thing that I can tell you is there is this region that is different, but then it's not very quantitative. Okay, it's not a linear increase, so it's not proportional increase. Now I want you to observe, keep in mind this region. Okay, let's say around 900 wave number. Okay, now there is not much difference. Now we can modify infrared spectroscopy slightly. Okay, instead of just analyzing the sample directly, we can do what is known as pyrolysis. Okay, if you remember thermogravimetric analysis lecture that I gave you, I talked about pyrolysis, where you break down molecules in the absence of oxygen, and the molecule breaks up, and based on what components come out, you can tell the composition. That's exactly what we are going to do here. So you take these two molecules, let's say separately, and then you do pyrolysis, then you lose hydrogen. Okay, and when you lose hydrogen, you form unsaturated carbon-carbon double bonds. Okay, here the background information that we already have is polyethylene, it gives vinyl groups. Polypropylene, it gives vinylidene groups. Okay, the difference here is the C double bond C. It's here, it's a CH2CH. Here there is no hydrogen here. Okay, and this small variation changes the way the CH2 stretch happens. Okay, now if you check the CH out of plane bending. Now for vinyl group it's 909 centimeter inverse, and for vinylidene group it's 889 wave numbers, centimeter inverse. Now we have this information in our back of mind. Let's take the mixtures of samples. Okay. Now I'm showing the spectra, different spectral regions of only this region zoomed in. Okay. So now let's say you take C3, which is polypropylene. You know, propylene, the monomer, it has 3 carbons. That's why they're calling it C3. So now you have 0% propylene, polypropylene, and you have 100% propylene. Okay, and if you see the 2 bonds that we discussed before, the bond CH out of plane band corresponding to vinyl and vinylidene group, you have one peak that is increasing in intensity as the component, the vinylidene component is increasing. Okay, does that make sense? It's very straightforward, right? So now based on this ratio of these 2 peaks, you can tell how much of polypropylene was there, polyethylene was there. And this is one place where we can slightly modify the sample and we can make this a quantitative process rather than just a qualitative process. Okay, so this is to summarize the study. So now based on the ratio of these 2 peaks corresponding to the CH out of plane band, you can quantify how much of polyethylene and polypropylene is there in a mixture of copolymer. Okay. Now the peak ratio gives you the idea. Okay, I'll summarize the first part of the lecture. Now we started with basics of how infrared spectroscopy occurs, how it is carried out. We saw what conditions a bond has to exhibit in order to absorb infrared radiation. We also saw the relationship between the frequency of vibration of a bond and also the bond characteristics. And we next moved on to a typical infrared spectrum where we saw absorption and transmission. There are 2 kinds of spectra, and we saw examples of vibrational modes, how one can classify them into infrared active, infrared inactive. We saw example of water, we saw example of carbon dioxide. This is a V-shaped molecule, this is a linear molecule, and we also saw one mode of carbon dioxide where because of its bending, it lost its linear shape and it became a bent molecule, and then it became infrared active. And then we saw examples of increasing complexity. We started with alkane, then we added a hydroxyl to it, we added a carboxyl, we added an amine. We also saw the effect of hydrogen bonding, and the conclusion from this is that you should not have any water. Okay, from these 2, the vibrational modes and simple examples, is that in your infrared samples you cannot afford to have any water. And we also saw this generalized table where we saw regions where different functional groups give absorption, and then we saw cellulose, and we saw one example where infrared spectroscopy was helpful to follow the reaction where the hydroxyl was converted to a trimethyl silyl group. And then we moved on to characterizing a nanoparticle reaction where we saw a cellulose nanocrystal being modified with a cationic surfactant. And then we moved on to characterizing a copolymer, polyethylene, polypropylene, where we used pyrolysis to convert polyethylene to vinyl group, polypropylene to vinylidene group, and that gave a difference in the peak intensity corresponding to the CH out of plane band, and that was the basis of quantitative characterization of this copolymer. I'll take any questions if there are. Do you guys have any doubts? Okay, then we'll have a short break, 5 minutes break. Okay. Okay, let's continue from where we left. Now, we've seen some examples of spectra, how to interpret spectra. okay, how to use infrared spectroscopy. Now I will talk about how the instrument works, okay, how do we record a spectrum. As we have seen before, okay, we have the outline of the setup here. We have a source of radiation, we have a spectral apparatus. Okay, this is the wavelength selector, if you remember the schematic that we learned in our second lecture. And then we have the infrared beam going through the sample, and the absorption happens if there are bonds corresponding to the frequency that is incident, and the transmitted beam is detected by the detector. And nowadays the detection process is also accompanied by a very powerful computer, which is as good as the computers that we use. Okay. For processing the data, I will tell you why we need a computer. And the source of radiation is generally something that is hot. As you all know, that hot objects emit infrared radiation. Generally it's a glow bar or a nuanced rod where it's heated to, let's say, around 1000 degrees or something close to that, and that emits infrared radiation. And it generally emits a range of radiation, and then you choose what you want using the spectral apparatus. Okay, and then when it comes to detectors, we have already seen this. Okay, you have thermal detectors. Because infrared radiations, the photons of infrared radiation, they are very low energy, so they can't produce photoelectric effect. They can't knock out electrons. So then what we do is we use the property of infrared radiation to heat up sample, and we use that property. So one is thermal detector, where you detect the change in temperature of the mass, and that, depending on how much infrared radiation is incident, that gives you a corresponding change in the temperature, and that gives you an idea about the intensity. And you also have photoelectric detector, where this doesn't work with lower frequency infrared radiation. Okay, this is more common to be used. Okay, so now we have seen the source of radiation, we have seen the detector, a bit about it, and we will see how the detector actually works, how it processes the data. Okay, so now if you remember the second lecture that I gave, I told you that there are dispersive components which spread the photons based on the wavelength, and you select the wavelength that is required. Okay, but then actually nowadays for infrared spectroscopy, nobody uses dispersive elements. We use what is known as Fourier transform. The difference is, in dispersive elements we measure one wavelength at a time. Okay, but in Fourier transform we send a whole bunch of infrared radiations at one go, and we later on analyze all the wavelengths together. So the difference between these two is, here you do high throughput, where you simultaneously measure several wavelengths. This is a bit tricky concept. Okay, I've given some links below. Here there will be a section called notes. Okay, some of you weren't there. I'll show you. Okay, if you see, next slide. If you see below the slide, okay, there is this section called notes. Okay, I give some links. Fourier transform is a bit tricky concept. Okay, even if you don't get it, that's not a big issue. Okay, but if you are more interested, you can go to those links. But I'll try to explain best I can. Okay. So an FTIR setup consists of the following. You have a source of light, okay, and you have a stationary mirror. This and you have a mirror that moves. Okay, so now the source of radiation, it produces a whole range of frequencies. Okay, and the incident radiation, it is reflected back, and the beam splitter, it sends it back. Okay, so now at this region, the reflected beam interferes with the incoming beam. Okay, now depending on how much distance the beam has traveled from this region to this region, it will undergo a path shift. Okay, and depending on how much path shift it has taken place, it will undergo destructive or constructive interference at this region. Different frequencies undergo different path shift. Okay, so now all that they do is you have a source of light which produces a whole bunch of frequencies, and this position of mirror, which is mobile, it's moved back and forth, and during this process you change the frequencies that undergo destructive interference, and you change some frequencies that undergo constructive interference. Okay, so now the light that is going through here after interference, depending on the distance, the intensities at different frequencies, it's changing all the time depending on the distance. The computer, what it does is it notes the precise position of this mirror at every time it's in motion, and it knows the different intensities the source is producing. Depending on the path length, it knows what is the expected interference intensity, resultant intensity. Okay, but then because of the sample interference, sample absorbs certain radiations. Okay, now the resultant absorbed radiation, it will introduce some variation in intensity other than the interference. So all the computer tries to do is, it has got the interference pattern, it has the knowledge of the interference intensities that is supposed to be there, but the sample has absorbed some radiation, so it tries to calculate what all frequencies has been absorbed. Now the difference between this and the dispersive way is, here at one go you're sending all the frequencies that you need. So here your function as a function of intensity is the frequency, but in the case of dispersive, you will actually change the wavelength. At one time you send one wavelength at a time. Okay. Okay, the next slide, maybe it will become a bit clearer. So now you have the intensity, you have the retardation, okay, which is the distance from the distance this mirror has moved. Now you have the intensity variation depending on the path length that the mirror has shifted the wavelengths. Okay, and different frequencies undergo either destructive or constructive interference. Okay, the summary of this slide, I would say, is instead of sending one wavelength at a time, you're going to send a whole bunch of frequencies, and the computer does the job. Okay, let's assume that. And if you need more information, or like I showed you the link, they have very detailed mathematical treatment, which is not necessary for this course at least. Okay, yeah. Okay, so now we are going to send an interferogram which has multiple frequencies, and you're going to deconvolute the interferogram and then get individual peaks. Okay, so now the advantage of an Fourier transform, FT stands for Fourier transform, it's the mathematical treatment that the computer uses to deconvolute the spectrum. Okay, that's why it's called the FTIR. If you observe, a lot of people in books, they no longer call it just infrared spectroscopy, they call it FTIR. Okay. So now FTIR allows detection of all wavelengths simultaneously, and before you used to use dispersive infrared spectroscopy, which was more time consuming, and it was mainly driven by increase in the power of computers, and now you hardly find dispersive infrared spectrometers. I think almost all spectrometers that I have come across all through my life, they are FTIR. Okay, so now let's go to how we make samples for FTIR. Okay, so now we generally come across three different types of samples. One is powder, either it can be rough, it can be a smooth surface, solid surface, and liquid. Now let's go one by one how sample preparation is done for infrared spectroscopy. One thing is, I've told you before, in all these samples you don't need water. Okay, you should not have water. That's a base condition for all these sample preparation methods. Okay. Okay. So now you should not have water, and compared to Raman spectroscopy, keep in back of your mind that you don't need sample preparation for Raman spectroscopy. Okay. Okay. So now there are three main ways of doing it. One is you take the sample and then mix it up with a matrix that is IR transparent. Okay. One is called forming a pellet, The other is called a mull, other is a neat. There are also ways in which you can measure infrared spectroscopy directly on the sample without any sample preparation. We'll go one by one what each of these mean. Okay, so now let's first talk about pellet. There are two important points that we need to keep in mind. One is alkali halides, for example, potassium bromide, sodium chloride that you guys, we all use in food. They have two important properties. One is they don't absorb in infrared region. Okay. The second, when you apply very high pressure, they become plastic. They become a pellet. Okay. So now, potassium bromide, it forms a pellet much easier when compared to sodium chloride. That's why we use potassium bromide very commonly. But the disadvantage is potassium bromide absorbs water from atmosphere more easily when compared to sodium chloride. Okay. So now if you want to make fresh sample, okay, then KBr is best. But there are situations where it's good to use sodium chloride plates. I'll give you examples where each of this is important. Okay. So now you have potassium bromide powder. You take your sample, which could be a powder, which could be a solid, but eventually you have to grind it into a powder. Okay. So now you mix the sample with KBr, and then you place the mixture here, and then there's a piston. You apply very huge amount of pressure, 500 to 10,000 psi, and under that pressure, the KBr, it becomes a plastic pellet. Okay. And you use that. You place that in the window. This is the path for infrared radiation in the spectrometer. Okay, so now you put this pellet here, and as the light passes through, you measure absorption. Okay, and this is mainly used for powders, solid powders. Now the next thing is mull. Okay, this is where you take a powder and you mix it up with a liquid. Okay, and generally, when you read in books, you'll find that it's always called new joule mull. Okay, that's how it has become the common name. It's like Xerox. It's photocopy, but then it has become, the name has become Xerox because it's a very famous company. Like that, new joule is a mineral oil. It's a brand of mineral oil, and in the beginning, everybody used to use this, and even in a lot of textbooks, you'll find people using the term new joule mull, but it's mull. That's the original name. Okay, so now what you do is here you take the sample, you mix it up with a bit of mineral oil and forms a paste, and then you put it on a sodium chloride plate and you spread it, and then you sandwich it with another sodium chloride plate, and then you put that in here, okay, in this place. Okay. The reason why here we are going to use sodium chloride, and in the previous case we used potassium bromide, is because this plate, you want to reuse it again and again. You can, okay? You just wash it off with some organic solvent, and you can again use this. Since we are planning to use it again and again, we want to use a material that doesn't absorb too much water. As I said before, the potassium bromide, the term used is hygroscopic, which absorbs water, okay? Sodium chloride is less hygroscopic than KBr, but the reason why we are not using sodium chloride in the previous case for making pellet is because you need much higher pressure. Okay, so you have to choose which is the sample preparation that you need. Sometimes this is better, sometimes the previous one is better. It depends whether you have the equipment. Second, whether the sample undergoes decomposition at high pressure. Okay, so it's mainly a practical choice. That's all. It's nothing to do with that much of chemical stability, more a practical thing. Okay, so you place it between the sodium chloride plates and then you do the measurement. Okay, next, what if you have a sample that is liquid? Then what you do is you take a sodium chloride plate, you put a drop of the liquid and you sandwich the liquid between two sodium chloride plates and you do the measurement, absorbance measurement. Okay, so now we have seen all the three methods where you disperse. So now if you see all three, you took the sample and you either put it in between two plates or you dispersed it in a medium like KBR. Okay, and like I said before, the advantage is you need very high pressure, and it's also hygroscopic. Water interferes with analysis, so if it absorbs water, that's going to turn up in your spectra. So it's KBR is a bit tricky. Okay, what about infrared spectroscopy without sample preparation? There are 3 ways we can do that. I'm going to talk about 3 ways, maybe there are more. Okay, one is based on total internal reflection. Okay, we'll start with that. The technique is called attenuated total reflection, ATR. Okay, and the whole process is dependent on total internal reflection. You have seen this principle in surface plasmon resonance, but we'll go through this again. Here the only difference is there is no plasmon, it's just an interface. Okay, so now let's say you have a source of light, and here is a boundary where the higher refractive index medium ends and the lower refractive index medium starts. In this case it's air, and in this side it's glass. So now as the angle of incidence keeps increasing, so now you measure the angle of incidence with respect to the normal to this line. Okay, so now as the angle of incidence keeps increasing, in the initial periods you have refraction happening, and as the angle increases, once it goes beyond an angle called critical angle, you have reflection happening. Okay, this is the angle above which there is reflection happening is called total internal reflection. Okay. Now I don't know if you know how optic fibers, how they work. So if you put another medium here, then it undergoes again total internal reflection here. So it keeps going like that. Okay? So it keeps traveling through the entire tube and it comes out from the other end of the tube. That's how optic fibers work. Okay, so now we'll go a bit deeper into what is exactly happening at this boundary. Okay, so now here this was the glass, okay, and this was air in the previous slide. Now, as I showed you, the reflection was happening, but if you zoom in and look at the electric fields, this is what is happening. You have a bit of electric field of the incoming radiation traveling into the neighboring medium. Only the electric and magnetic field. Okay, there is no transfer of energy at this point. Okay, there are conditions where the energy gets transferred, but if you take only total internal reflection, there is no. It's only the field that propagates. It propagates and then it goes back when it is reflected. Okay, that wave, which is the momentary existence of the electric magnetic fields on the opposite side of the medium, that's called an evanescent wave. Now, it's called evanescent because the word means vanishing. Okay. Now, if you look at the electric field intensity, as a function of distance, if you move from this boundary up, the intensity falls exponentially. Okay, that's why it's called an evanescent wave. The overall conclusion from this slide is that when there is internal reflection, okay, you have a bit of electric field of the reflected beam propagating into the next medium. That's the conclusion from this slide. Now, as we all know, the propagating electric field, it's fluctuating dependent on what frequency it is. Okay, so now if you have any bonds that are in this region in the medium, if the frequency of those bonds, fluctuating electric field created by that bond, if it matches the frequency of this incoming radiation, it's going to be absorbed. Okay, it's simple infrared spectroscopy, but here it's depending on the electric field generated by the evanescent wave. Okay, so this is what is absorption by molecules during this process, during reflectance. Because it is getting absorbed, that's why we use the word attenuated, because the intensity is lost. Okay, so now you have the setup is as follows. You have the high refractive index medium, you have the lower refractive index medium, and as the total internal reflection happens, the distance over which the evanescent wave travels into the lower refractive index medium is denoted by dp, and that's, if you see, directly proportional to the wavelength. So the higher the wavelength you use, the longer it travels into the lower refractive index medium. Okay, keep this in back of mind that a part of electric field propagates into this medium as an evanescent wave. That's all we need to remember from this slide. Now, if there are, if we are sending infrared radiation, okay, of specific wavelengths, and if there are bonds that can absorb infrared radiation, the intensity of this light that is getting reflected will decrease, will get attenuated. Okay, and based on how much absorption is happening, you can tell whether the molecules are there or not. Okay, and one more level of knowledge to this setup. In actual ATR setup, what is actually presented is squares of places where the total internal reflection happens. So you put the sample over this place, and the sample, let's say you can take paper, okay, the paper you guys are writing, powder it, make a fiber mesh out of it. You can put the fiber on this, okay, and the fibers will make contact at this, on these squares at random points, and so those fibers will constitute this region. You understand this? What is your sample going to be? Your sample is going to be in this region. If you put your sample on this, and during the total internal reflection, the evanescent wave gets absorbed if there are bonds, if there are molecules that can absorb. Okay, so now you put the sample, and if you have absorption, you see the spectra, and you use Fourier transform for this as well. Okay, so now you can use powder, you can use solid, for example, pulp or paper, and the big advantage of this ATR, IR is that you don't need any sample preparation. This is almost like Raman spectroscopy, where you just take any sample that you want. But condition number one, no water. That's the only condition. Okay. The analysis is fast, and you can select the locations which enable mapping. One other disadvantage of this is, if you see the setup, like I said, if you put the sample is going to be in contact with these regions at random places. Okay, the sample is not perfectly flat. So if you take out one sample and you put another sample, you can't guarantee that the number of contact points, the amount of contact will be exactly the same. So there will be some variation from one measurement to the other. Okay. And that's one disadvantage of ATR. Okay, you can analyze powders and solids, as I mentioned before. Okay, one other facility that you can add to this is a microscope. So other than measuring infrared spectrum, we also would like to see where we are measuring the spectrum. Okay, for that, what some companies have done is you attach an infrared spectrometer to an optical microscope. So first you see where the measurement is happening through the optical microscope, and then you rotate the whole objective setup so that the infrared spectrometer setup comes into focus. Okay, this is one good way of being sure where you're doing the measurement. Here is the actual setup. Okay, I think this is an instrument that is available in VTT. Okay, the other type of direct measurement. Okay, so now we are dealing with techniques that allow us to measure infrared spectroscopy without sample preparation. Okay, so now this technique is called photoacoustic spectroscopy. It's a very simple technique. In our department, we have this actually. So we have an inert gas here. As I told you before, infrared rays have this property of heating up sample. Okay, and now you place the sample here and you shine infrared radiation. If you see, this region is sealed, okay, but then it's transparent. The seal is transparent to infrared radiation. As the sample heats, it generates pressure waves. It creates a difference in pressure, and that difference in pressure can be detected by a microphone. It's just like how the normal microphones work. It detects change in pressure as we talk. The same principle. And if the sample is absorbing more, the pressure change will be higher. That means the wavelength that is being absorbed at that radiation is higher. And this again can be used for analyzing powder, analyzing salts. Okay, so now the other technique that is also very useful is diffuse reflection. Very often our samples, for example, if you take paper, if you take a sheet of fiber, it's not very smooth, and this technique allows us to detect infrared absorption on very rough surfaces, and this is how it works. Now if you take a very smooth sample, we know the angle of incidence is equal to the angle of reflection, okay, the laws of optics. But then if you take a rough surface, the beam is pretty much spread out, it's scattered in all directions. Okay? So now this challenge of how the beam is spread out is dealt as follows. You have a hemispherical reflecting device. Okay, so now you have an infrared source, it's reflected, and no matter which direction the light is dispersed, there will be a spread of radiation in all sorts of directions. And this hemispherical focusing surface will focus all the reflected radiation, doesn't matter which direction they come from, it will get focused to this detector. And one important thing about the diffuse reflection infrared spectroscopy is that you have both reflection and transmission happening, all processes, it's a mix. If you observe this, the beam in this part is going through, but then here it's getting reflected. Okay, so it's both transmission and reflection. And during the transmission, the infrared radiation can get absorbed, and that again gives us idea about what kind of bonds are there inside the sample. Okay, diffuse feeling. So, for example, if you have a powder, okay, or if you have a solid, then what we can do is for drifts, this technique, you can powderize the sample and then disperse it in a volatile solvent, put it on a shiny surface, and then you can measure diffuse reflectance from even a powder. Okay. And one last technique that I'm going to talk about is reflection absorption infrared spectroscopy. To be specific, how polarized light is getting reflected. Now, polarized light is where the electric and magnetic fields are vibrating only in one plane. Okay, the light that we generally come across, the vibrations are in all directions. But polarized light, the vibrations are happening only in one plane. Now, if there is, I will give an example. Okay, now, if there are molecules, if, for example, this is alkane thiol. Okay, now it has CH2 groups continuously bonded to each other, and then there's a thiol. I'm representing this molecule by this schematic diagram here. Now, it is well known that this molecule on gold, it self-assembles at an angle 30 degrees. On the other hand, on silver, it self-assembles at an angle 10 degrees. Now, if you send a polarized, now we'll go back, okay? Or we'll go back. Now, we send a polarized beam. Now, the vibrations in this beam, they're happening in only one plane. Now, the molecules that are present on the surface, if the vibrations of that molecule are aligned with the vibrations happening on the incoming light, the light will get absorbed. Okay, if the plane, the molecule that is exhibiting vibrations, if the vibrations are happening in a plane perpendicular to the incoming polarized light, then it won't get absorbed, even though it's in the same wavelength as the frequency that is absorbed by the bond, but the angles are changed. That's the only difference. Okay. So here is one example where if you send polarized light, and if this was the plane of vibration, okay, let's say the plane of vibration is horizontal to the, this is not true, I'm just giving an example so that you guys understand it. Okay, let's say the vibration is parallel to the surface. Okay, now because here the tilt is higher, okay, now the polarized light will be absorbed more by this because this is closer, more parallel to the surface, closer to being parallel to the surface, and this is farther away, closer to being perpendicular to the surface. Okay, so this is one example where even the directional vibrations can be detected, and this gives more information about how the molecules are oriented, not just if the molecules are there, not just how much of these molecules are there. You can also tell whether they are tilted, whether they are vertical with respect to the surface or not. Okay, here are some good reading materials if you want to go into a bit more detail. Okay, and I'll summarize this lecture. First, we started with basic instrumentation, where we saw different infrared sources and detectors, and we saw the difference between dispersive and Fourier transform. Dispersive, you measure one wavelength at a time. In Fourier transform, you simultaneously measure all the wavelengths. And we next moved on to sample preparation. 3 types of samples: solid, powder, liquid. Okay. Now, when it comes to dispersing sample in IR transparent medium, we have 3 types. One is making a KBR pellet, the other is Nujol mull, where you take a liquid mineral oil and you disperse the powder in that, and you sandwich that between 2 sodium chloride plates, and you use that for measurement. And you have a neat, which is the actual liquid. You don't mix it with anything, but you take 100% liquid, then place that in between 2 sodium chloride plates. And next we moved on to 3 techniques where we don't need any sample preparation. Okay, one is attenuated total internal reflection, where we depend on the evanescent wave propagating into the lower refractive index medium. Okay. And then we moved on to photoacoustic spectroscopy, where we used the change in pressure caused by the temperature difference, and that was used for detecting the absorption. And we saw diffuse reflectance, where the absorbed radiation due to either from rough surfaces can be focused to one place using a spherical mirror. And finally, we saw reflection absorption, where we can use polarized light to get idea about orientation of molecules. Okay, if I can feel that I didn't explain well the reflection absorption. If you guys want, I can explain that again. Is that clear? Is the reflection absorption, is that clear? It's not, right? Okay, I'll go through once again. Okay, so now I'll just draw this, it's easier. Now you have a light beam. Okay. Now the electric field, it's propagating in a plane. Okay, it's propagating in a plane. But then the white light, the light that you normally see, this propagation is happening in all directions. It's not only in one plane. Okay, but then polarized light is one where all the vibrations, the electric field is happening only in one plane. Okay, the vibrations are in one plane. Now, as I told you, if there is a bond, okay, let's say a CH stretch, it's happening. The bond also has a plane, okay, and when the electric delta minus delta plus, okay. Now, depending on the relative angle between this, the field generated by this has a plane. The bond is vibrating in a plane. It's vibrating in a plane, and the electric field of the light, that is in a plane. They both have to be related to each other. Only then it can absorb. The good thing about the light that we sent in the previous cases, not the polarized light, the normal light, is the vibrations are happening in all planes. Okay, it's a mixture of all planes. And so you don't have to worry too much about the angle of this plane and the angle of this plane. Okay, there will always be some light waves that have intensity in the right plane. But then you can do a very specialized spectroscopy where the light is polarized. Okay, so the frequency is fixed. The frequency is fixed. Okay, and we also fix the polarization. Okay, then the only thing that decides whether how much these two interact is the relative angle between these two bonds. The plane in which this bond is present and the plane of vibration of the electric field. Okay. So now, in the case of now, in this case, let's say you're sending a polarized light and it's getting reflected. Now, the molecules here, they are at 30 degrees. Okay. On the other hand, in this case, there are 10 degrees. So now this bond. Okay. So in effect, what we are changing now is because of the tilt angle change, this bond orientation is changing. Okay. Because of that, the efficiency of resonance between these two will change. So the molecules are there, the bonds are there, but the angle between the incoming plane of polarization and the plane of vibration, that's different. And with that you can detect whether the planes, how tilted they are. The bonds, in fact you're not detecting the molecules, the bonds, how tilted they are. And this study is from this article. Okay, if you want. Okay, it's a very difficult article. I can tell this already. Okay, you have to find references. You have to go back. Okay, from this article, it's a far more complicated study than what they did. What I'm presenting here, I'm presenting only, let's say, 5% of complexity of what they actually dealt with. Okay, now I'll take. Is that clear now? Did that help? Okay. I'll take some questions if there are any. You have any doubts? But you guys get the overall picture, right? Where Raman is, where infrared spectroscopy is, okay? And every time you finish, a technique, just go back and think about it. You know, how does XPS is, what kind of information you get from XPS that is different from Raman and FTAR? Okay, these are the kind of questions you'll get asked. So maybe it's better if you guys discuss with each other. Okay, and let's say you take a problem. Like let's say I'll give you a piece of paper to analyze. Find me what is this about. Now how will you go about? Okay, let's say you get a piece of paper. What kind of information you get from XPS? What kind of information you get from FTIR? What kind of information you get from Raman? Okay, go through this process mentally. Then you will understand what technique to use for which purpose. That's the whole purpose of this course, is to make you understand if I give you a problem, you guys should be able to choose a technique or a handful of techniques where you get the information that you're looking for. Let's say you paint paper, okay, and you want to find out some property of paint. What kind of techniques you use. Okay? Yeah. But do think about it, okay? Do think, and then that's how you will understand. There is no book that will tell you this is the technique for this. There is no algorithm. Okay, it's our choice at the end and our convenience. But I am considering one more discussion like we had before. Okay, maybe at the end of all lectures. Okay, so that you guys get time to read through, and then we will sit down like what we did before. I'll give you a couple of questions and then we can discuss. Okay. Okay. Did I summarize? I summarized, right? Okay. Next week, okay? Next week, on Monday you'll have surface plasmon resonance. On Wednesday you'll have quartz crystal microbalance. On Friday you'll have atomic force microscopy. One thing is, when it comes to your experimental exercise, you will do atomic force microscopy, surface plasmon resonance, and quartz crystal microbalance. You will get a demonstration. Okay, you will go and see how the techniques are done, but then you won't use them for your experiments. Okay. Yeah. Thank you. No, that's why I told you, you have to get your I'll just stop the video.
Yes.
It's around 2 gigabytes.
Yes, I hope it's my drive is enough.